Okay, this is Math 1090, section 1.6, Modeling with Linear Functions. Today we're going to talk about supply and demand, and then also cost functions, revenue functions, profit functions, break-even, also market equilibrium. So let's do some definitions first. The cost function expresses the total production costs in terms of the amount of items produced, or Q. The total cost includes both the fixed costs, which are the startup costs like equipment and buildings, and the variable costs, which are the costs that depend on the number of items produced or the amount of service provided. So total costs are simply defined to be your fixed costs plus your variable costs. Okay, next is the revenue function. R of Q is the product of the price per unit times the number of units sold. So revenue is simply just the price you charge for your product or service times the quantity of products you sell or services you provide. Okay, profit now. The profit function, P of Q, is the relationship between a company's total profit and output or quantity produced. So it equals total revenue minus total costs. So profit is simply just revenue minus costs. It's the amount of money coming in to your company minus the amount of money you spend. Okay, now the next two definitions refer to the idea of supply and demand. Okay, we're going to talk a little bit about supply and demand today. When you graph a supply curve and a demand curve on a set of quantity and price coordinate axes, the two curves will cross, okay? And where they cross, we call that the equilibrium point, or the market equilibrium. And this market equilibrium, it's a point on a graph, so it has two coordinates. One coordinate is the equilibrium price. So this is the market price where the quantity of goods supplied is equal to the quantity of goods demanded. So this is the point at which the demand and supply curves in the market intersect. Okay, we also have the idea of equilibrium quantity. The equilibrium quantity is the quantity that exists when a market is in equilibrium. Equilibrium quantity is simultaneously equal to both the quantity demanded and the quantity supplied. In a market graph, the equilibrium quantity is found at the intersection of the demand curve and the supply curve. Okay, so I've drawn a little picture down here at the bottom of the page here. This graph on the left demonstrates a basic demand curve in blue and a supply curve in green. Okay, notice on these axes, the horizontal axis is labeled with Q, or quantity, and the vertical axis, the output, is labeled with price. Okay, so both demand and supply relate quantity to price. Okay, but it's just from a different perspective. The demand curve is from the consumer perspective, whereas the supply curve is from the producer perspective. Okay, so take a look at the green curve. If the price for a product is zero, clearly no one's going to want to produce or supply that product to the market because you get nothing for it. Okay, there's occasionally exceptions, to this. But we're not going to go into. This is not an economics class, so we're just going to look at it from a mathematical perspective. Okay, so, but as price increases, the quantity that will be produced and supplied to the market will be increasing as well. And as the price goes up and up and up and up, people are more willing to produce more and more and more because they can fetch more and more, a higher and higher price on the market for their product. Okay, whereas demand, so supply has this positive correlation or positive relationship between quantity and price. Okay, as price increases, quantity increases, or vice versa as the quantity. Okay, whereas demand, the demand curve always has a negative correlation between price and quantity. So when the price is really high, consumers don't like to buy a lot of that product. They'll try and get by with as little as they can typically. But when the price goes low, sometimes consumers will say, oh, wow, this is really cheap. Maybe I'll stock up on it. And so there's this negative relationship between price and quantity from the consumer perspective. Okay? So that's why in any supply and demand curve graph, the two curves should cross at a point somewhere. Okay? And the supply curve will always be pretty much trending upward. The demand curve will trend downwards. Okay, so that's the idea of equilibrium price and equilibrium quantity. What about the break-even point? So the break-even point refers to the idea of cost function, revenue function, and profit functions. Again, the break-even point represents the sales amount. Sales amount and revenue are often conflated as being the same thing. They're not necessarily the same thing, but so the break-even point represents the revenue that is required to cover the total costs. Another way to think about this is also when the total profit is zero. Okay, so let me show you a graph that illustrates the idea of the break-even point. So this graph over here on the bottom right, we've got two curves here. The green curve would represent revenue for a company, and the blue curve represents costs for that same company. Okay, now profit is what? Profit is revenue minus costs. So you're only making a profit when your revenue curve is higher than your cost curve, aren't you? When it's the other way around, you're losing money. So the break-even point represents the point where you first start becoming profitable, where you first start making money. Okay? When your quantity is somewhere between 0 and the break-even point, you're losing money. Okay, so the break-even point is where revenue and costs become equal for the first time, and then any quantity you sell beyond that will be profitable. Also on the you see this blue curve, the cost curve, its y-intercept represents the fixed costs. That's how much you have to pay in order to produce your product before you've even produced a single one. This is the price you have to pay for equipment, maybe a building, etc. Okay. All right, let's move on. Okay. First exercise. A tech startup is looking at developing and launching a new mobile app. Initial development of the app will cost $300,000, and they estimate marketing and support for each user will cost 50 cents. While the app will be free, they estimate they will be able to bring $2 per user on average from in-app purchases. How many users will the company need to break even? Okay, so we're going to do this in 3 parts. Part A, write the total cost function and the revenue function. Okay, so the cost function, I'll write that as C as a function of Q, quantity. Well, let's see, they have some initial upfront cost to develop the app. That's $300,000. And then they figure they estimate marketing and support for each user cost 50 cents. So it'll cost about 50 cents to acquire each user of the app. So that'll be plus 0.5 times the quantity of apps downloaded. What about revenue? Well, they expect to bring, they estimate they will be able to bring in $2 per user on average from in-app purchases. So on average, for each new user they have, they get $2. So 2Q. Okay, write the profit function. Remember, profit is just revenue minus total cost. So P as a function of Q, this is equal to R of Q minus C of Q. This is the definition. What is this? Our revenue is 2Q. And an important thing here is I want to wrap the expression that represents my cost function in parentheses, because I want to subtract off the entire expression. So I'm going to put parentheses here and then write down my cost function, which is 300,000 plus 0.5Q. Okay, now we can simplify this, and when I distribute the negative sign to both terms in the parentheses, I get a negative 0.5Q, and I can combine that term with the 2Q term. 2Q minus half a Q is 1.5Q, or we'll say 1.5Q. So I'll come over here. P, profit, as a function of quantity, is going to be 1.5Q minus 300,000. Okay, what is the break-even quantity? Again, break-even quantity occurs when the profit is first 0. So we want to set the profit function equal to 0, solve for Q. Oops, it should be 1.5Q minus 300,000. Okay, so add 300,000 to both sides, and I get 1.5Q is equal to 300,000. Divide both sides of the equation by 1.5, and I get Q is equal to 300,000 divided by 1.5. Well, dividing by 1.5, that's 3 halves. And dividing by 3 halves is the same as multiplying by 2/3. So I'm just going to rewrite this as times 2 over 3. Now 3 goes into 300,000, and we're left with 100,000. So 2 times 100,000 is 200,000. So the quantity is 200,000. So we need 200,000 users of our app before we expect to break even with this app. Okay, that's good to know. Next exercise. Your company is considering adding a new product line. The accounting department has determined that the cost function for this new product will be, so we're using X here for quantity. That's okay. So C of X will equal 205X plus 3,900. So the 205X, that's the variable costs. It depends on how many items you produce. And 3,900, that's the fixed cost part of the cost function. Okay, and the revenue will be R of X is equal to 255X, where X is the number of units sold, and both cost and revenue are in thousands of dollars. The sales department expects to be able to sell around 85 units. What is the break-even quantity? Okay, so we need to create the profit function, set it equal to 0, solve for X that gives us that break-even quantity. Okay, so let's see. First, we'll start with cost. We're given the revenue and cost function, so we can go right to the profit function. The profit function, recall, by definition, this is something, if you get nothing out of this class, I want you to remember that profit is revenue minus cost. So, what is this? Revenue is 255x. And we'll put parentheses around the entire cost function. This is 205x plus 3900. Okay, let's simplify that a little bit. 255x minus 205x, that's 50x. Minus 3900. Okay, now I want to set this equal to 0 and solve for x. I get 50x equals 3900. So, if I divide both sides of that equation by 50, I get x equals 3900 divided by 50. I can divide both sides. I can cancel out a factor of 10 from both the numerator and denominator there, and I'm left with 390 over 5. How many times does 5 go into 390? I'm just going to pull up the calculator real quick. Let's see, 390 divided by 5, 78. So this is equal to 78. Okay, so that's our break-even point. That's the quantity we have to sell. Up until that sales level, we're not making money, we're losing money. But at that point, we've made $0. So the question is, should you go ahead with the new product or hold off? Okay, so this is a subjective question. So clearly, if the sales department expects that we can sell 85 units, then since 85 is greater than 78, we will make a profit. Okay, we will make a profit. But what will that profit be? Well, let's see. The profit at a production level of 85 sales is going to equal, well, our profit function is 50x minus 3900, so it's going to be 50 times 85 minus 3900. What is this? This is going to be 50 times 85 minus 3900. Okay. 50 times 85 minus 3900 is 350. So, okay, now remember, this is in thousands of dollars. So we're going to make a profit of $350,000. Now that sounds really good. That's a lot of money. But how much do we have to invest before we can even begin making the first product? Well, our fixed cost is 3,900 times 1,000, right? Because our cost function and our revenue function, they're both in units of thousands of dollars. So that fixed cost of 3,900 actually represents 3,900 times 1,000, or $3.9 million. Okay, so we're going to have to outlay $3.9 million in order to make a profit of $350,000. That doesn't sound so great. Okay, and you know, what if we're not able to sell 85 units? then if we can't sell at least 78 units, we're going to lose money, and that would be very bad, perhaps even disastrous. So there's a lot of factors to take into consideration when making these decisions, obviously, but perhaps maybe your company strongly believes that this product will grow and sales in the future will grow as well, and maybe you just need to get a foothold in the market and it's worth the risk. Okay, but perhaps if you're facing uncertain times, uncertain economic times, and if that were the case and you're not sure about sales in the future, maybe you expect the economy to take a downturn or something, then maybe it would be wise to hold off a year or something before embarking on this new product line. Okay, so I'm just going to leave the answer with it depends. Okay. Certainly $350,000 of profit is great, but in relation to $3.9 million of initial outlay, it's not a lot of money. You would expect to be hoping to make a lot more money probably before you commit to such a ambitious endeavor. Okay, next exercise. Okay, so this is much more down to earth and much smaller numbers here. Okay, still fun though. Suppose you begin selling keychains at a local Pokemon convention. Your cost for each keychain is $2.05, plus you have to pay a fixed weekly fee of $250 for the booth. Your plan is to sell the keychains for $3.75 each. One of the things I love about this is that it doesn't matter what your business is. You could be selling Pokemon keychains or selling products that cost thousands of dollars. The same mathematical principles apply, right? Okay, part A, write a function C of n to represent your total costs for the week if you sell in keychains. Okay, so remember, total costs is fixed costs plus variable costs. And we're going to use in here instead of Q or X. We're just trying to get you guys used to using different symbols for your variables. Okay, so cost as a function of number of items. Let's see, you have a fixed cost of $250 for the booth. So this will be $250 plus, and it costs us $2.05 for each keychain. So if we multiply that by the number of keychains that we buy from our supplier, then that's going to be our variable cost, right? So that's going to be 2.05 times n. That's the cost for all the keychains we order from our supplier. Okay, part B, write a function R of n to represent the revenue from selling in keychains during the week. Well, we charge $3.75 for each keychain, right? Remember, revenue is just the price you charge times the quantity you sell, and we're selling in. So our revenue as a function of n will be $3.75 times n. Part C, write a function P of n that represents the profits from selling in keychains in a given week. Okay, so remember, profit is revenue minus costs. And our revenue is 3.75 n. Our cost function, we want to wrap this in parentheses, remember, is 250 plus 2.05 n. Okay, now I distribute that negative sign to both terms inside the parentheses and I get a negative 2.05 n, and I want to combine that with positive 3.75 in. Can I do that in my head? 3.75 minus 2.05 is going to be $1.70. So we're charging $1.70 over the price we pay for the keychains. So $1.70 times in minus $2.50, the booth cost. That's our profit function. All right, part D, how many keychains must you sell to break even? Well, here we just set the profit function equal to 0, solve for the quantity. 1.70 in minus 250 equals 0. We break even when the profit first becomes 0. We get 1.70 in equals 250, or n is equal to 250 divided by 1.7. Let's get the calculator. $250 divided by 1.7. Looks like about 147 and 6 cents. No, this is a quantity, so just a little greater than 147. So we'll say 147.06. $147.06. So the number of keychains you sell in order to break even has to be greater than or equal to, well, let's just say greater than 147. Okay. Let's see here. So suppose a baseball team plays in a stadium that holds 64,000 spectators. With the ticket price at $11, the average attendance has been 25,000. When the price dropped to $8, the average attendance rose to 32,000. Find the demand function d of q that describes the price as a function of the quantity Q of spectators. Okay, so this is a supply and demand type of problem, and we are given some data points there, aren't we? So Q is going to represent the number of people in the stands, the number of spectators, and this demand function will relate quantity to price. Okay, and notice we have a couple data points here. We're told that when there were 64,000 spectators, or sorry, no, I guess that 64,000 is an unnecessary number in the word problem, isn't it? The next sentence is really what matters here. With the ticket price at $11, the average attendance has been 25,000. Okay, so let's make a little table here that relates quantity to price. And price. So we know that when the price is $11, the quantity of spectators is 25,000. And when the price dropped to $8, the average attendance rose to 32,000. Okay, so find the demand function that describes the price as a function of the quantity. So we have these two data points, and we want to, let's assume that the demand function is linear. It changes linearly with quantity. So how do we get a linear function if we have two data points? First, we want to get the rate of change, and then After that, we'll use one of our data points and that rate of change and plug it into the point slope form to get the equation of the line. So recall, slope, in this case our output variable is price, and so we have delta P divided by delta Q, or P2 minus P1, the difference. We use delta to remind us it's a difference. The difference in prices divided by the difference in quantities, so Q2 minus Q1. Okay, I'll call this point 1 and I'll call this point 2. So then price 2 is 32, price 2 is 8, price 1 is 11, quantity 2 is 32,000, quantity 1 is 25,000. Okay, let's simplify this. We get, in the numerator, we're going to get negative 3 over, let's see, 32 minus 25 is 7,000. Okay, there's our rate of change. Now we need to plug this and a point. We'll pick the first point into the slope, point slope form to get the equation of the line. In this context, the variables we're using are P and Q, so P is the output, Q is the input. So the point slope form would be P minus P1 is equal to M times Q minus Q1. So we get P minus price 1 is $11. The slope is negative 3 over 7,000. Q minus Q1 is 25,000. All right. Now we need to simplify. First thing I'm going to do is distribute that slope to both terms in parentheses on the right hand side. And we end up with P minus 11 is equal to negative 3 over 7,000 times Q. And then let's see, we're going to get plus 3 times 25,000 is 75,000. And it's positive 75,000 over 7,000. I can cancel out those zeros with those zeros, and I'm left with just 75 over 7. I want to solve for P, so I'm going to add 11 to both sides of the equation here, and I get P is equal to negative 3 over 7,000 Q plus 75 over 7 plus 11. But I want a common denominator here so I can add the constant terms together. So 11 is equivalent to 77 over 7. So let's just write it that way. And now we can add those two together, and we're going to get, let's see, 75 plus 75 would be 150, but I got to add on 2 more, so 152 over 7. So our function is, so the demand as a function of quantity, which gives me the price, is this function. It's going to be negative 3 over 7,000 times Q plus 152 over 7. Okay. this is a demand curve. Does it have a negative slope? Yeah, it does. Okay, that's good. Demand curves should always be trending downward. Okay. Exercise. I've added a little table here that we'll fill in because there's a lot of numbers floating around in this problem. Just in these notice in both of these problems, what have I done? I've created a little table, and you'd be amazed at how helpful just a small little table can be in helping you to organize the data, because when the numbers are buried in the verbiage of the word problem, it can be extremely hard to extract the correct number out sometimes, or it's very easy to pull the wrong number out. So I really like to put these numbers into a table so I know what I'm talking about. Okay, let's read this exercise. At a price of $160, there is a demand for 1,736 and a supply of 800 items. Okay, we don't even know what we're talking about, but it doesn't matter. At a price of $300, there is a demand for 616 items and a supply of 1,500 items. Assuming supply and demand are linear, find the equilibrium price and equilibrium quantity. Okay, so in this problem, it looks like what we want to do, but we want to find the equilibrium price and quantity. In order to do that, we need to have the demand function and the supply function find the quantity at which they're equal, where they cross. Okay, so let's see here. The first sentence tells us that it's got three numbers in it. At a price of $160, there's a demand for 1,736 and a supply of 800. So when the price is $160, the demand is for a quantity of 1,736, whereas the supply will only be 800. However, when the price rises, and now in the next sentence, we get the next bit of data. At a price of $300, there is a demand for 616 items. So when the price goes up, demand goes down. But when price goes up, supply goes up, right? 1,500 for the supply. Okay. There we go. We've got a little table here. Notice though, however, this table's a little backward. I have price coming before quantity. That's how I normally think of it, but in economics it's almost always, these supply and demand curves are almost always graphed with quantity on the horizontal axis and price on the vertical y-axis. The way I've written it here kind of implies that price would go on the horizontal axis and quantity would go on the vertical axis, but and you can do that. There's nothing wrong with graphing or thinking of it as quantity depends on price. Okay, but typically these graphs are done with quantity on the horizontal axis and price on the vertical axis. Okay, so we'll think of our demand and supply functions in that way, where Q is the input and price is the output for both supply and demand. Okay, so what we need to do is come up with the equation of two lines here. So we need to get two slopes. I'll call the first slope m sub s for the slope of the supply curve. Okay, this is going to be let's see, we're thinking of price as depending on quantity. So the output variable is price. So this is going to be P2 minus P1 over Q2 minus Q1. Let's see here. We'll call this first row 1 and the second row 2. So the second price is 300. The first price is 160. The second, okay, now this is for the supply curve, so now I'm going to look at these numbers in here. Wow, that's weird. Why did it do that? Okay. So Q2 is 1500 and Q1 is 800. Okay, 300 minus 160 is 140. 1500 minus 800 is 700. I can divide out a factor of 10 in both numerator and denominator. 14 and 70 are both divisible by 7, and I get 2 over 10, which is the same as 1 over 5. So the slope of the supply curve, it's positive, that's a good thing, and it's 1/5. Okay, now the slope for the demand curve, I'll call that M sub D. Okay, again we want the difference in prices, P2 minus P1. I don't need to write all this. I'll just put a little double tick mark to indicate it's the same as above. Okay, but we're going to actually use different quantities here. We're going to use the column of quantities for demand, but the numerator will be the same. It'll be this 300 minus 160 over, but now the numbers will change. The quantity 2 for demand is 616, whereas quantity 1 for demand is 1,736. So here we get 140 over 616 minus 1736. I'll get the calculator out for that. (616 minus 1736). Negative 1,120. So we end up with 140 over negative 1,120. I can divide out a factor of 10 from both numerator and denominator. And I have, let's see, I have negative 14 over 112. These are both divisible by 2. I get negative 7 over 56. Oh, these are both divisible by 7, and I get negative 1/8. So M sub D is negative 1/8. Okay, that's a good sign because our demand curve has a negative slope. All right, now we need to come up with the supply and demand functions and set them equal. Okay, a lot of work in this problem. So let's start with supply. In this context, the point slope formula would be P minus P1, because price is the output, is equal to the slope of the supply curve times Q minus Q1. Okay, let's see here. What do we get? This is P minus 160 is equal to 1/5 times Q minus Q1, and this is for the supply curve. Q1 for the supply curve is 800. So we get P minus 160 equals 1/5 Q minus, how many times does 5 go into 800? I want to say, my brain is not working so well. 800 divided by 5. 160. Okay. So 160. Oh, look at that. The 160s will cancel. When I add 160 to both sides of the equation, I'm left with P is equal to 1/5 Q. Or in other words, S of Q is equal to 1/5 Q. So now we have the supply curve. We need to do the same thing and get the demand curve. Again, we'll use this point slope form. P minus P1 is equal to M sub D times Q minus Q1. So we get P minus 160 is equal to negative 1/8 times Q minus, now this is, I got to use Q1 from the demand column. Q1 from the demand column is 1736. Okay, let's simplify. P minus 160 is equal to negative 1/8 Q, and it'll be plus, what is 1736 divided by 8? I think I'll just use the calculator real quick to do that. 1736 divided by 8, 217. So this is going to be plus 217. Now I add 160 to both sides, and I get P is equal to negative 1/8 Q plus 217 plus 160 is going to be 377. Or in other words, my demand curve, demand as a function of quantity, is equal to this negative 1/8 Q plus 377. Okay, we're not done yet. What we need to do is set these two functions equal to each other and find the quantity at which they're equal. So we want to solve 1/5 Q equals negative 1/8 Q plus 377. Okay, I will add 1/8 Q to both sides of the equation, and I get 1/5 Q plus 1/8 Q equals, oh, this should be 377, sorry. 377, I don't know what I did there. 377. Okay, 1/5 Q plus 1/8 Q. I can factor Q out, and I need to add 1/5 plus 1/8. Well, the common denominator here would be 40. So I'm going to get 8 over 40 plus 5 over 40. This will be times Q equals 377. 8 plus 5 is 13. Multiply both sides of this equation by the reciprocal of 13 over 40, which is 40 over 13. So I end up with Q is equal to 377 times 40 over 13. I don't see any common factors there, so I'll just use the calculator. 377 times 40 divided by 13. So clear. 377 times 40 divided by 13. 1160. So we know the equilibrium quantity now. What about equilibrium price? Well, you got to remember the price from both functions will be the same, so it doesn't matter which function we use to evaluate the price. But since the supply function is so much simpler, I'm just going to use that. So I'll do it over here. P is equal to 1/5 times 1,160. I could probably do that, but I'm just going to use the calculator. 1,160 divided by 5 is 232. So then our equilibrium is the point Q quantity comma price, which is going to be 1,160 comma 232. Okay. So I've graphed this problem. Let's take a look at that graph. I used Desmos.com to graph this problem earlier, and indeed you can see that Desmos is really nice. You can put in functions using the variables you want to use. So I put in the supply function here, which is 1/5 Q, and the demand function. And then I put in this point, the green point here, which is at 1,160 and 232. That is indeed on at the point of intersection of both the supply and demand curves, and then I plotted all the data points that we use to generate those curves, those lines, and indeed they are on the line. So okay, so what does this mean? It means that at a price of $232, the market will supply and demand 1,160 items. All right, one more page here. Alex is choosing between two moving companies. The first, U-Haul, charges an upfront fee of $20, then 59 cents per mile. The second, Budget, charges an upfront fee of $16, then 63 cents per mile. When will U-Haul be the better choice for Alex? So we have, it looks like cost functions, right? There's a fixed cost for each rental, and there's a variable cost based upon miles that you drive. So let's see here. Let's create two cost functions, and clearly both cost functions are going to be increasing functions. The more you drive, the more miles you drive, the more it will cost. But one's going to have a steeper slope than the other, and so at some point they'll cross, and at that point, that's where that will be the point where U-Haul will become the better choice, because notice Budget, the upfront or the fixed cost of $16 is cheaper than U-Haul's $20. Okay, but Budget charges 63 cents per mile, whereas U-Haul only charges 59 cents per mile. So U-Haul is probably better for longer trips. Okay, well, let's find out exactly though how far you have to go for it to matter. So we need a cost function for each company, one for U-Haul and one for Budget. So let's do U-Haul's first. I'll say C sub U for cost function for using U-Haul, and let's just use maybe X for miles. Okay, so this is going to be the fixed cost of $20 plus 59 cents per mile. I'll write that as 0.59x. So that's the cost function for U-Haul. What about the cost function for budget? I'll call that C sub B of x. The fixed cost for budget is $16 and then 63 cents per mile, so this will be plus 0.63x. Okay, and what we want to find out is x, the number of miles, such that the cost will be equal. When are they first equal? So let's set these two functions equal to each other and solve for x. So we're doing c sub u of x equals c sub b of x. So we have 20 plus 0.59x equals 16 plus 0.63x. Okay, I think I will subtract 16 from both sides of the equation, and I get 20 minus 16 is 4, so I'll get 4 plus 0.59x will equal 0.63x. Now I think I'll subtract 0.59x from both sides of the equation, and 63 minus 59 is 13 minus 9 is 4. So when I subtract 59x or 0.59x from 0.63x, I'm going to be left with 0.04x. So I'm left with 4 equals 0.04x. Okay, so divide both sides of the equation by 0.04, and I get 4 divided by 0.04 equals x. Okay, I could just chuck that into the calculator, but hey, I don't need to do that. Remember, this is equivalent to 4 divided by 0.04 is the same as 4 100ths, or 4 over 100, right? So 4 divided by 4 over 100 is the same as 4. This is the same as 4 times 100 over 4. Dividing is the same as multiplying by the reciprocal. So those cancel, and I'm left with 100. There we go. X equals 100. So if Alex is going to be traveling more than 100 miles, he should choose U-Haul. If he's going to be traveling less than 100 miles, he should choose budget. When hired at a new job selling Audis, you are given 2 pay options. Option A, a base salary of $16,000 with a commission of 9% of your sales. Or option B, a base salary of $25,000 with a commission of 5% of your sales. Okay. Now the question is, in order for option A to be a larger total salary, how much would you need to produce in sales each year? Okay, so we're selling cars, right? And so part of our pay is a fixed quantity. This is like the cost function, right? It's a fixed amount. And part of our salary depends upon how many sales we make, how much we sell. Okay. And it's a percentage, right? We make a percentage of the sales. So if I do $100,000 in sales, 9% of that would be $9,000. Okay, so it seems to me that you could use X to represent sales, our yearly sales, how much we sell each year. Okay, so let's let X equal sales, or maybe total sales would be the better choice here, in dollars. Okay, and then so we need maybe two functions here that are going to relate the total amount that we sell to our salary. So this is kind of interesting. This is a function that relates dollars to dollars, but that's perfectly fine. There's no reason why you can't have a function that has the units of the input are the same as the units of the output. Okay, so let's see. I'm going to call these functions S sub A and maybe S sub B, S for salary. So let's see, S sub A of X. This is going to be, well, in option A we get a base salary of $16,000 each year. So this is going to be $16,000 plus then the commission part of our salary, and 9%. Remember, if I change that to decimal, that's the same as 0.09. So part of our salary will be 0.09 times the amount sold. Now this is X is not the amount of cars we sell. It's the total sales figure, right? You take the cost of all the cars that you sell during the year, add that all up, and that's X. Okay. Okay, similarly, what about option B? Our salary under option B will depend upon the total sales that we make for that year, and this will be 25,000 plus 0.05x. Okay, and then the question is, well, clearly option B is better if you don't make a lot of sales. You know, if you don't sell anything, well, you're a lousy salesman, but option B is going to be better, right? Because you're going to make 25,000 versus 16,000. But at some point, at some level of sales, option A becomes better. So we have to set these two salary functions equal to each other and solve for the X value where they first become equal. In other words, the total amount of sales that you have to make in order for the two salary options to be equal. Okay, so let's do that. Let's set S of A equal to S of B, and we get 16,000 plus 0.09x equals 25,000 plus 0.05x. Okay, I'm going to subtract 16,000 from both sides of the equation, and 25,000 minus 16,000, well, that's the same as doing 25 minus 16, that's going to be 5 and then 4, so 9,000. So I have 0.09x is equal to 9,000 plus 0.05x. Now I need to subtract 0.05x from both sides of the equation because I want to get my x terms on the left and my constants on the right. So 0.09x minus 0.05x. I'm going to think of it like money. 9 cents minus 5 cents is going to be 4 cents. So this is 0.04x is equal to 9,000. So x is equal to 9,000 over 0.04. 0.04, I can write that as 4 over 100. And dividing by a number is the same as multiplying by its reciprocal. So this is equal to 9,000 times, okay, the reciprocal of 4 over 100 would be 100 over 4. 100 over 4, though, is just the same as 25, so 9,000 times 25. Can't do that in my head, really. 25 times 9,000. $225,000. So let's just write that out. So X equals $225,000. Okay, so I have to make $225,000 in sales. That's when the two options are equal. $225,000 in sales. How many Audis is that? I think an Audi, I don't own an Audi, and I've never purchased one, but probably about a $40,000 car. So let's see, 225,000 divided by 40,000 would give us the number of cars approximately. So let's divide this by 40,000, and we get 5.625. So about 5.62. So not about. It's exactly 5.625 $40,000 cars. So if you can sell 6 cars or more, then option A is better than option B. 6 cars or more, that's one every 2 months. I don't know anything about car sales, but I would imagine that's pretty doable. So there we go. So notice how math can help us figure out all sorts of different things in life, like which offer to take. Okay, and this concludes section 1.6.